How does the human brain make decisions? What processes are happening that cause you, or you cause, this is the difference between free will and determinism, which is a topic of a later video, that cause you, once again, to make decisions? To fully answer this question lies outside the scope of this video. But in this video, I'll be attacking a very specific part of the human decision-making process, the basal ganglia. The basal ganglia is essentially an action selection system. So there are a lot of systems in the brain. The fear system, the feeding system, and all of these systems are vying for control. All of these systems are vying for which is going to be activated and which is going to be power in the brain. And the action selection system, the basal ganglia, is connected to all of these systems. And then it decides which one is in control by sending inhibitory signals to all the other systems that it doesn't want to be in control. Through this process, it's able to decide which system is in control. The basal ganglia's function has been replicated in spiking neural networks, which are neural networks based off and inspired by how the brain works. And so action selection is literally the entire field of reinforcement learning. Reinforcement learning is just trying to figure out which action you should do given which circumstance. And possibly with a system that is inspired by the brain, these neuromorphic systems based off the basal ganglia could be more effective than current reinforcement learning agents. A group of researchers used a system inspired by the basal ganglia to control an unmanned aerial vehicle, and it was successful. I wrote a simple algorithm that implements basal ganglia action selection with Nango FPGA. Here's how it works. The autonomous agent implements a basal ganglia action selection system which uses reinforcement learning on an FPGA ensemble, which is the Nango architecture. It can perform 3 actions: go forward, rotate clockwise, and rotate counterclockwise. And it has a 5-point radar that provides it the distance to any obstacles directly ahead, to its sides, and etc. So it uses this input of its 5-point radar to determine which 3 actions to perform, similar to how the real basal ganglia action selection system decides which systems to activate given similar input values. A reward system is set up to give a positive value when moving forward, and no reward if the agent is stationary or has crashed into a wall, which in theory will drive it towards constant motion without ever hitting a wall. The reward system computes an error signal for each action, which is the difference between the computed utility and the instantaneous reward. The computed utility is the reward that the system predicts it will get based on its action, and the instantaneous reward is the reward that the system actually gets. By feeding the error signal into the FPGA ensemble, the system learns to associate specific radar states, which once again is the 5-point radar state that I talked about earlier, with the actions that provide the highest reward. This process is similar to how the actual basal ganglia action selection system works. In the future, brain-based artificial intelligence may take a huge role in our lives. Because they are neuromorphic and based off the brain, they may be more reliable than their pure neural network counterparts.